So we're writing dissociation reactions. And Calvin, if you point up there, so for Ian, on review day, what we usually do is we write down what kind of problems you're going to have. So for their particular test, they have 3 dissociation equations, which are what they're doing right there. And then we're going to go through the other types of problems here, and the point values are listed too. Okay. All right, so let's see what we got here. We got some problems. Let's go through this. You guys are good. Let's see what we got. All right, so first of all, if you're going through a dissociation equation, what should the state be for the initial thing? This should be a solid. Okay. Now, a couple problems here. One more problem here. Because he has Fe as a +3. Okay, and I'm going to tell you that that's not right. Okay. Now, one way you could do this, right? One way you could do this is to go look at your periodic table. And when I go look at my periodic table, I see iron can be +3 or +2 when I look at the oxidation state. So that means I have a problem. I got to figure that out. So what you really have to do, the only way you can do this, I'll show you a shortcut later, but we haven't learned that shortcut yet, is this. You know SO4 has to be a -2 because that's on your polyatomic ion sheet. This thing has no charge. Therefore, iron can't be +3. It must be what? +2. It's got to be +2, so that +2 cancels out that one. So that's +2. So I'd say, like on a 5-point problem, he would have probably lost 2 points on that. All right, so that would have been. Now this one, we got some problems, right? Yes.
Wait, why is it 2 over 3?
What's that?
Why is it
It's got to be +2 because these 2 charges got to cancel out because this thing has no charge. If this thing was FeSO4 +1, then this would be +3, and that'd be -2. Now this one here, whenever you see lots of atoms, you're probably dealing with a polyatomic ion. So we've got KMNO4, and this has got to be a solid, so we're missing solid. Yeah, you're putting it into water. Well, it breaks up into 2 pieces. Well, what 2 pieces? K and MnO4, which is a polyatomic ion on your sheet that's negative. Potassium's group 1, so it's +1. And since these are dissolved, they're both aqueous. Okay. You know, if you need more of those to do, somebody's just got to post something on in Modo, and I'll give you more.
Just for the sake of the question,
Mm-hmm.
if the O was separate, the subscript 4, that would go in front of the O, right?
It just can't happen. And let me just say it that way. I know what you're saying, okay? Yes, but it can't happen. Okay?
What do you mean? Can't happen.
If O splits off, it's actually going to split off as O2.
Oh,
So it'd be 2O2.
okay, so say it was like phosphorus instead.
Yeah.
Then it would be. Okay.
Yeah. But even then, phosphorus would probably be P4. That's what I'm saying. I know what you're saying. And yes.
Okay.
Yes. It would come out as a coefficient. But it just can't happen in this particular instance.
Okay.
So, like if it was Na3, it would be 3Na+.
Okay.
Right. Okay. So first thing I would say is, if you don't know how to do that, that's going to present problems for you here for sure. Okay? Because that's concentration of ions is dependent on you being able to write a dissociation equation. So like for this one and for that one, for every one of these, you get 2 of these, right? 2 ions, so it's a 2 to 1. Can we move on? Because that stuff will come up again in other problems. Right? So just to be clear too, remember this is you take a solid, you put it into water, and the reason it breaks down is because our crystal, like here's an NaCl crystal, each one of those atoms gets surrounded by a sphere of water. Remember, water's got that V shape like this. Here's a water molecule, and in this there's an oxygen and 2 hydrogens, and these 2 hydrogens are sharing electrons with that oxygen. But this oxygen's like Big Brother, he's a bully, and he steals the electrons more of the time, and these guys are like the little brothers, they get the electrons less of the time. So more of the time the electrons are up here, less of the time they're down here. So more of the time this is slightly negative and this is slightly positive. Slightly negative N can interact with positive charges, slightly positive N can interact with negative charges. So we get bubbles of water forming around those ions. And you get that until all the water is taken up and then you can't dissolve anymore and we say it's saturated. Okay, so let's see. Okay, let me do it like, I think I'm going to do it this way. I like this better. So this will take me 2 seconds, but I like it when I can put the actual problem right up on the board, so I'm going to do that real quick. So this is, should have had this ready, but such is life. Textbook, 7th edition, open, page 171. Okay. Okay. Yeah. Okay, let's see. Click. Okay, you're gonna wake up, good. Okay. All right, there you go. All right, so let's get some guys up here. What do I do with my cards? Here you go. All righty. All right, first one, Jarrell. Come on up and do something productive. I want this on the cleaner. Something productive. Oh, by the way, I'm sorry. I cut off a little bit too. The original thing says calculate the molarity of each solution. That's what it says at the beginning of the problem.
What's the molarity
Yep, it says calculate the molarity. So I'm kind of giving Jarrell a hint right now. Calculate the molarity of each solution. Jarrell, check it out. Calculate the molarity is what it says before. That's not written down here. So what can we write down if we have to calculate the molarity? Jarrell, I'm trying to give you the answer right now. Calculate the molarity. What's that mean to do? No. Guys, listen up.
Yeah, I don't know.
It tells you to calculate the molarity.
I don't know how to do that.
I know. But you know what you're being asked, right?
Kind of.
What am I asking you?
Calculate the molarity.
Okay, so let's write that down, that you want to figure out what molarity is. No, what's the letter we use for molarity?
Right?
Is that a lowercase or an uppercase?
Lowercase.
Nope.
No?
Okay, equals. There you go, question mark. Okay, so you did something productive, right? Calculate the molarity, all right? All right, Carson, something useful. No, I'm not arguing with you because you do need to do this, but how do you know you need to do this? Wait, I'm asking.
You need to do 184.6 of that times 1 mole of the starter.
Yeah, but why?
To find the mole.
And why do you need moles? You're not wrong. You're right, but I'm just asking you why. I'm wondering why you jumped to that first.
In case you need to find moles of solution over.
There you go, because you're looking ahead, right? So let me just make a point here, because what I'm saying is this, is that when you write down M equals, and I knew Jarrell was kind of a little bit lost there, it means moles of solution per liter, right? So now Carson's looking at this and saying, well, I know I need to get moles, all right? And I can see I have a mass, so I know I'm going to need molar mass. I'm going to calculate molar mass. Make sense? Now, the way that I would go about this is what I suggest to most of you guys, is first read through the problem and find all your questions and all your data first. You get what I'm saying? Get organized first, then start doing calculations. But I'm not going to argue with him. This is fine. You can go ahead with what you're doing. But do you guys get my point? Find what's in the problem first before you start calculating things, because maybe you don't need to. Maybe it's in the problem. Maybe it's something that they're not asking for. There's one up there someplace, probably underneath my book right there. Probably under the lid, I would suspect.
112.
I always take math like that and break it down into two things, 7 times 10 is 70. 7 times 6 is 42. I can do that in my head a lot quicker. Okay, so what are the units for that, though?
Star grams.
Okay, what is that?
Just grams.
Grams,
Over. Mole.
moles, yep. Okay, all right, Adam Upperman, something productive.
Oh, do that too.
What we gonna do? Ooh. Ooh, no unit?
What?
No unit?
Oh,
Whoa, MG. Ooh, we're not going to be able to do that. Why not? What's this written in terms of? And that is?
MG, so you got a nice.
So what's the problem we have? Change milligrams into?
We have 294.
I don't think we want to go there either.
I have no idea what to do.
Well, you would know what to do if it was just grams, right?
Yeah.
So what do you got to do before you go and do that step? You got to take milligrams and turn it into. No, we're not ready to use that yet.
I have no. So I put grams and milligrams. I know that. So like,
Okay, so
how
you're
am I
in
supposed to write
milligrams.
that?
You're in milligrams. You want to turn it into. Let's just build off of what you got. Let's get rid of this here.
4,
Look at this.
16 milligrams
Okay.
times
Times. Get rid of.
milligrams.
Turn it into. Wait. Let's just get the.
1 gram.
Okay.
0.001.
Nice. Okay. Now, you could stop and get that number, right? But there's no need to because we don't need that number.
Can I just keep going?
Yeah, you could just keep going. You want to show them what we're talking about here?
So I can just write what I was going to write with
Yep.
1 mole.
Exactly.
Okay. 1 mole.
Now we're in business. Okay, so let's take a look at this, everybody. You're good job. I'm just gonna get rid of this. So look, you still got to know how to do your metric to metrics, right? Because this didn't come out to be the units that we wanted. So again, what are we trying to accomplish here? We're trying to get moles per liter. That's what we're focusing on. And right away we saw we need moles. Well, if I knew I needed moles, I would say, well, I have a mass that gets me to moles. It's 184.6 milligrams, but I got to be in grams. So a gram is 1, milli is 0.001. Remember, we flipped that. And then I would need star grams, was it Carson got that for us? Yeah, Carson got that for us. And so now we could do this calculation, and when we do this, milligrams are going to cancel, grams are going to cancel, and we're in moles now, right? So we've got part of it. We just got to do the calculation to get this. Now we're looking for something else too. And so we'll leave that to Rob Harris to do something productive here.
So if it asks for, like, define concentration, that's the same as molarity?
Molarity is concentration, yep. So you got a couple options of what you could do here, Rob. What do you want to do?
Just going to use the admin.
Sounds good. No. You want liters here, right? You want milliliters down here to cancel, right? Now wait. What's the meaning of liter? No prefix. Milli means 0.001, so you put milli up there. What's the meaning of liter? One. So that should be, no, that was right. We need 1 on the bottom. We're flipping it. That says that there is 1 milliliter is equal to 1,000th of a liter. That's correct. Yep, there you go. Okay, so check this out. Milliliters is not the unit we want. We want to be in liters. So he starts out with his 500 milliliters. He multiplies it by milliliter on the bottom, so they cancel or reduce to 1. Liter on top. Liter has no prefix. That means 1. It's a base unit. Milli means 0.001. He writes that up top. Multiply across to get 0.5 liters. So we got our liters now. We still need our mole answer there. So we'll give that to Garrett Height. Absolutely.
There's 7 questions tomorrow, that's it?
Yes. And that first one's just like 3 short ones.
That's the H2O?
Yep. Give me a little number, isn't it? pretty little, right? 0.1 divided by 200 or 300 almost.
I feel like that's not right.
Should be a pretty small number.
Let's just be,
That seems reasonable. All right, yeah. I mean, I'll double check it, but I was thinking it would be pretty darn small.
0.00.
Or you can write it like that. Either way is fine. So I got 184.6 times 0.001 equals to 294 equals. And I get 0.000627. Is that what you got? Yep,
Yeah,
that's good. That's a perfect place to round to. And then units. Okay. Now, Matt Barry, you want to bring us home?
Do you want me to label the?
I think it's better to do that. Now, I just kind of was looking the other way. I was going to summarize it at the end, but I think that's a good point you're making. Good.
And then base liquid.
That sounds good. Good. Okay. So just a couple things. One, I think some of you guys have a good plan of attack for these problems, some not as well. That's just what I was hoping. Just was hoping I would do that. Try that again. Hey, it came back. Okay. So my plan attack would be this. Now again, I don't have the original part of the problem here because of the space, but I'll show you that. I'll fix that next problem. It originally said for A, B, and C, calculate the molarity. So as soon as I see calculate the molarity, I probably would have wrote molarity K2CR2O7. I probably would have labeled what I'm calculating the molarity of, because it could be the concentration of a particular ion or all the ions, right? So by first just identifying what it is you're looking for, that's important. So again, then that would mean I'd need moles over liters. And then I would read through and I'd say, well, I've got a mass here. That's just as good as getting moles. And so then I would probably run down this path right now, right? And then I keep reading and I'd say, oh, I got 500 milliliters. Well, that's giving me liters. So I'd run down this path. And then I just plug in. I think it is a good idea, though, to keep that K2CR2O7 with it. So that's a very straightforward calculate molarity problem. Okay, we good here? Okay, so if calculating molarity, you're looking for moles, you're looking for liters, you're looking for moles of whatever it is you're talking about. All right, now let's look at this problem here. Okay, now, again, this cuts off, I understand. It says calculate the concentration of all ions present in the following solutions of strong electrolytes. Okay, now again, the word strong electrolytes here, that just means everything's going to dissociate. Everything's going to break apart. And I want you to do it for just D. So we're calculating the concentration of all ions. So there you go. All right, so if we're calculating concentration of all ions, that's the first thing we need. So why don't we address that? And that'll be for, how about John Lupo? If you have to calculate the concentration of all ions, what are you going to write down? Calculate the concentration of all ions.
What's your rate distillation equation?
Even before that, the question says calculate the concentration of all ions. That's what you're being told to do. Last time we wanted to calculate the concentration of K2CR2O7, so we wrote down M equals, right? If you're trying to calculate concentration, what are you calculating? What is concentration? That's not what it's asking for. It's asking for the concentration of all ions, not the concentration of the ammonium sulfate.
So it'd just be moles over
Moles of what?
all ions?
Ions, yep. Okay. All right, so Andy Burns, wouldn't it be a day without calling Andy up to the board? All righty, Andy, what can we do now?
Figure out the ions and ammonium sulfate.
You can do that. There should be sheets there, yeah.
Kind of put it over here.
Sure, sure. Now, wouldn't we want to write those next to each other in crisscross?
Oh, yeah.
Wait, what did you do there?
Crisscross, I don't know.
That's not crisscrossing. Crisscrossing says you take the absolute value of the charge and cross them, making them subscripts.
Why did we crisscross?
Because you got to know what the chemical is. And now we can get the number of ions, because unless we crisscross, we don't know how many ions are coming off of there. Now you can either stop there or you can keep moving on with that dissociation there.
Well, there's 3 ions, but I don't really know what to...
Okay, so if you know there's 3 ions by looking at that, that's fine. But do you realize that's going to kill you up here, though?
Yeah.
Right? So how about for just the sake of completeness, you're good. All right, you could answer, you know there's 3 ions. That's important to know. But Bo, can you show us how that would break apart? Yes, Garrett.
So for every concentration of ion problem, we have to crisscross like that?
If you're given the name.
Okay.
Now, if you're not given the name and I give you the formula, you could just go and do what Bo's doing right now,
Okay.
the dissociation part. Now, be careful too. You know, we had problems where we said concentration of all ions, right? But we also had problems where I'd say calculate the concentration of the ammonium ions. You get what I'm saying? Now that would be 2 for 1. If I do all ions, it's 3 for 1. If I did sulfite ions, it'd be 1 to 1. Make sense? So just pay attention what you're calculating the concentration of. There you go, you caught it. Okay, so that's good. So, you know, this step right here of crisscrossing, going from here to here, is only necessary if they give you the name. But if I gave you NH4 parentheses 2 SO4, then you would have to be able to figure out that there are 3 ions. So like Andy said, oh, I know there's 3 ions. So that helps them with this question, but it doesn't help them back up here at dissociation where you're going to have to write these types of equations. Okay. All right, John Vergotz, where are we going to go next? Yes, Jake.
So before we do the dissociation, we have to crisscross and then.
If I gave you the name of the compound. If I didn't give you the name, I gave you a formula, then it's already done. Yeah.
So if you give us a formula, it's always going to be done?
It would already been crisscrossed. Yeah.
Okay.
Yeah. Let's not lose sight of what we're trying to accomplish here, John.
I know.
Look at what we're trying to calculate. What is it we're trying to calculate?
The concentration of all the ions.
The concentration of the ions. So what 2 things do we need to know the concentration of the ions?
The moles of all the ions and
The moles of the ions over liters. So do we have any of those yet? Don't have either of those? We don't have moles of ions. I agree with you there. Do we have liters of solution?
yes.
Yes. How much?
Oh, we have 1.5.
So we could write V equals 1.5 liters, right?
Yes.
That's something to get out of the way. And now we know what we got to focus on, right?
No, we don't know the moles yet.
Right. Don't know the moles yet. Peter Frasina's not here. So Liam, John's got us our denominator. We don't have a numerator. How are we going to? Where was our starting point to get to that moles of ions? There's only one other piece of information, and it should be able to be linked to it, right?
So the final answer doesn't have to be over just 1.
It's always over 1 liter. Once you divide it out, it'll.
Change that?
Well, you divide it,
Oh.
and that'll reduce it to 1. I don't know about that. Liam, what are moles? Dozen, but a hell of a lot bigger, right? So we want to get to a counting number, right? How do we count atoms? What's one way to count atoms? By how can I count up oranges really fast, or how can I count up elephants really fast? No. How can I count nuts and bolts very fast if I want to count millions and millions of them all at once? Anybody want to help them? Weigh them. So we have a mass, right? We have 132 grams. So let's get rid of what you got there. And let's start out with our 132 grams. And what substance do you have? Yeah. And how are you going to turn grams into moles? What do you need to know? If I want to count up, say, oranges really fast, what do I have to know about each orange? how much each one weighs. So how are you going to find out how much an NH4SO4 weighs? Now the only problem you got there is you're probably going to run into that in a second with your calculation. So you might want to do that off in a scratch area someplace, like down and away. Because once you start doing this calculation, it's going to stretch over into here is what I'm saying. Okay, once we do this step, we'll turn it into moles. And then we're going to multiply it by what? 3 moles of ions over 1 mole of ammonium sulfate. So we should probably get, let's see, 132 grams. This thing probably weighs, let's see, 14, 28. Okay.